Minsky got an even better lower bound in terms of epsilon again. All right, so back to the lottery. It turns out there are plenty of samples. Our colleague Joe Killian ran these things, ran the samples through and found that an incredibly close fit between the number of collisions you should have had and the number that he got. So maybe the data was fudged to be too good, but it was really very close. Okay, so now we talked about the question of testing whether P is uniform or not. What about any other arbitrary distribution? It turns out that it's nearly the same complexity to test if P is any other known distribution. And we'll call this testing identity. It's really just based on a reduction. Okay, so if Q is some known distribution, I know its probability on every element. So let's say that's Q for now, okay? Now, for the purpose of this slide, but the algorithm doesn't actually need to do this, just for the slide, let's sort Q, okay? All right, so we just relabeled Q so that Q is monotone, and I know Q, so I can do this relabeling. I know I can write down what the relabeling should be, okay? So we've got that in our heads. And now notice, we're gonna partition the domain so into order log n groups so that in each group, based on Q, the values of Q differ by at most a 1 plus epsilon multiplicative factor. Okay, so in these groups, Q looks almost uniform. Okay, so there's about log n groups, and in each one, Q is very close to uniform. So this is what our test is gonna be. We're gonna take samples from P. Okay, and now since we know for each sample of P, based on the element that we know from Q, we know which one it should have landed in. Okay, so we'll put them into the buckets according to how Q bucketed things. And then we'll test that P is close to uniform in each group. And secondly, we'll test that P assigns approximately the correct total weight to each group. And if it passes these two tests, we show that P is actually quite close to Q. Okay, so what we've done is we've reduced this identity testing problem to something like order logarithmically many uniformity testing problems. And that's, so basically the complexity is within a logarithmic factor of this problem. Okay, let's look at a problem where both P and Q are given by samples. Okay, so now both P and Q are given by samples. I have no idea what Q is anymore. I just get samples from it. I still want to distinguish the case when P is equal to the Q from the case where P and Q differ by epsilon in L1 distance. What do you think this complexity is going to be? Rudin? Who thinks Rudin? Nobody. Okay, good, thank you. But it's n to the 2/3. Okay, so thank you, because I also thought it should be root n, and I didn't understand what was wrong in my calculations, and I kept thinking I'm making stupid mistakes, and then it turned out I wasn't. I just wasn't getting it because it wasn't right. Okay, okay, so the right answer is n to the 2/3. And why should it be so much different? Okay, so first I should say we were shocked. We did not expect this, but that's what happened. But why would it be so much different? Let me try to explain at a high level why it should be different. The reason is we already saw that collision statistics are really all that matter. Okay, because otherwise you can just randomly relabel. The names can't matter because you can randomly relabel the names. And the algorithm still needs to work. So it can't depend on the names. Okay, but collision statistics are really all that matter. You can construct distributions where there are heavy elements, and these heavy elements can hide all the collision statistics in the rest of the domain. These heavy elements roughly have probability 1 over n to the 2/3. Okay, so they have a lot of collisions, but they don't have enough so that you see any one of them too often. Okay, so you can't tell this is a heavy element, this is a heavy element. You have no idea which collisions came from heavy elements and which collisions came from lighter elements. But there's so many of those heavy element collisions that they're clouding all your collision statistics on the lighter elements. Okay, so then what you can do is you can construct pairs of distributions where the heavy elements are identical, but the light elements are either identical, in which case you're supposed to output pass P equals Q, or the light elements are very different, in which case you're supposed to output fail, P is very different from Q. But you can't tell the difference between the two cases because the whole difference came from the light elements, and their collision statistics got totally swamped by the collision statistics of the heavy elements. And that's why this is a different sort of a beast than the case where you actually know Q. Okay, what about additively estimating the distance? We're now, up until now, we've been separating close to epsilon far, okay? And in the slides, I wrote P equals Q, but you could slightly nudge it up to P is very close to Q, like epsilon over square root n close to Q. But the question is, can we get estimates on the distance, like additive estimates on the distance between P and Q? Can we, for example, distinguish P and Q are epsilon close from the case where P and Q are 2 epsilon far? Because maybe I have two distributions where I kind of expect them to be a little bit different, but I want to know if there's been a big trend change instead of just knowing about any trend change. And that seems like it should be an important problem. What would the complexity of this problem be? Unfortunately, it's much bigger, but it is still sublinear. Okay? And that's thanks to Greg and Paul Valiant. I have to say their first names because I don't want you to mix them up with the other Valiant. But there you need theta n log n samples. This is actually, I think, 2 papers. It's incredible work. It's really a tour de force. And so the moral of, I think, all these slides up till now is collisions tell all. The algorithms use collisions to determine wrong behavior, like too many collisions would tell you how far that you're far from uniform. But in this result here, to additively estimate the distance, and a few other results that I'm going to mention due to the Valiance in later slides, they actually use linear programming to determine if there is a distribution with the right collision probabilities and the right property. Okay, so it's a really nice work. For lower bounds, as we saw, collision statistics are the only relevant information. The problem is these collision statistics, they're not all independent, so they're quite difficult to work with. Again, the Valiants have helped us along and given us tools that we've used. I'll mention some of their results, but also other results built up on their works, and have given us generalized central limit theorems for generalized multinomial distributions. Okay, I'll mention a couple of results on information theoretic quantities. What about entropy and support size? I think we're all interested in entropy, so I don't have to give examples about why entropy is interesting. But when we worked on this, I was at NEC, and I had everybody at that time at NEC Research had to have both a computer scientist, at least one computer scientist and at least one physicist evaluating their work. And in my case, I had Bialik evaluating my work, which was really nice because it turned out he worked on the same problem. And this is why he worked on the same problem. And we only found out about this because of the evaluation. So it shows that sometimes it's good to get evaluated. They were interested in determining whether there's information in neural signals. They were trying to see, does this particular neuron respond to that particular edge detection? And each application of a stimuli gave a sample of the signal, but they never got exactly the same thing. So they couldn't really, it wasn't like a 0-1 learning case. So what they did was they estimated the entropy of the discretized signal in order to figure out which neurons responded to the stimuli. Now, when you discretize the signal, if you discretize too far apart, you lose having a good approximation of the signal. On the other hand, if it's too close, then your domain size blows up exponentially. It's horrible, right? So they're very interested in entropy approximation, which is sublinear in the size of the domain. Here's another example of why you might be interested in some of these information theoretic quantities. And let's start with multiplicative approximations. can you get it? So for entropy, can you get a multiplicative approximation of entropy? The answer is no, but really for the stupidest possible reason, it's because of the zero entropy distribution and the really tiny entropy distribution. How do you distinguish? Because what if I took samples from my distribution and I saw the same element many times? I don't know if I should take a few more samples and finally see the other element, or can I just say entropy 0? And I don't know when I can stop. Okay, but that's sort of, let's rule that case out. And let's assume the entropy has some minimal, sorry, that the distribution has some minimal entropy. Then it turns out you can gamma multiplicatively approximate the entropy with O tilde of n to the 1 over gamma squared samples. As long as the entropy is at least 2 gamma over epsilon. And in this, let's just take an example of gamma. Gamma is something that's bigger than 1, so think of gamma equal to 2. It means I can get a 2 multiplicative approximation of the entropy in n to the 1/4 samples. Okay, so so there's some hope if you're willing to accept multiplicative approximations of the entropy. And actually this is known to be tight, again due to Valiant. You can get better bounds when the support size is known to be small. And I should mention that also for estimating support size, you can get very similar bounds. Okay, what about additive approximations for entropy? Here, it's just like the case of testing closeness. You need n over log n samples. Okay, so what about testing whether a joint distribution is independent? So what I want you to get from this slide right now is only that the first coordinate of the joint distribution is from a domain of size n. The second might not be from the same domain. Okay, so the second coordinate of the joint distribution might just be a bit, or it might be also between 0 and n, or anything in between, and let's, without loss of generality, assume that n is greater than or equal to m. Okay, so what we want to know is whether our joint distribution on pairs is independent. It turns out that the sample complexity here is really weird. It's n to the 2/3, m to the 1/3. Remember that n is greater than or equal to m. That was just, that was our assumption. And so when n is equal to m, this just is order n, or square root the domain size. Okay, and this is known also to be tight. So that's just sort of another weird fact about testing independence. Lots of other properties have been looked at. Limited independence, many people in the theoretical computer science community are interested in k-wise independence and epsilon k-wise independence. Those are approximations to k-wise independent distributions. The testing so the supports required to generate k-wise independent distributions are exponentially smaller. The testing problem is also exponentially faster. K-flat distributions, these are, for example, k-histograms, k-modal distributions, all kinds of sort of shape properties of distributions like monotonicity, and properties of multiple distributions. All of these problems have been considered. There's many other problems to consider. Higher dimensional flat distributions, mixtures of k-Gaussians. There's so many properties, and I'm sure that you guys have even more options than I can think of at this point. There's been a lot of work at trying to get past these lower bounds, which are quite onerous sometimes. Even n over log n is better than n, but you would want to get around that if you can. People have looked at special distributions, other query models. For example, on the Google Ngram, you have all the frequencies are given to you, so you can just query the frequencies, and you can also get a random sample. Now, for many problems in that model, you can get exponentially faster algorithms, so why not? So that's another model that people have looked at. Competitive classification and closeness testing is something that people looked at in saying, okay, in general the problem is hard, but maybe for these classes of distributions you can do better. And what, so trying to find special cases where we can do better is an area of active research. But also, what about other properties to look at? And what happens when you can't even assume the samples are IID? Okay, so hopefully in this talk, which I've surveyed at pretty much everything, hopefully I've convinced you that for a lot of these problems, we need a lot less time and samples than you might think. And hopefully I've at least managed to convince you to check out that there's a lot of cool ideas and techniques that have been brought to the community by the various researchers in it. And I feel very honored to be among these people. And that there's also lots more to do. There's a lot of beautiful open questions. Okay, so I have one final open question in distribution testing. All right, and that's the price of the talk.
Thank you. We have time for a few questions. Before we start with the questions, though, I just want to remind everybody that tomorrow the program's a little unusual, and the plenary talk is actually in the morning by David Hausler at 8:30. Okay.
Is there a class of distributions like the uniform one you can, with Ronitt samples, proximity to?
Yeah, I don't know of any such result. I don't know of any such result. But it's a good question. Are
there any further questions? Okay, let's thank the speaker.